Welcome back to Deep Dive. Today, we're looking at something really special. Something literally from outer space. A piece of the Campo del Cielo meteorite. If you've ever held one, you know what I mean. It feels ancient, incredibly heavy, dark. Just this dense piece of cosmic history found down in Argentina. So our mission today, we want to trace its journey, from its birth way back billions of years ago to crashing onto Earth. We'll dig into the science it holds, its cultural importance, which is fascinating, and maybe surprisingly, the real challenges in just keeping these things safe. We've got a stack of sources here, articles, research papers, our notes, and we think there are some genuinely surprising facts, maybe a few aha moments for you. Ready? Okay, let's start with the basics. Campo del Cielo. What exactly is it we're talking about? And the name itself, Campo del Cielo, what's that mean?
Right, the name translates beautifully to heaven's field or sky field. Speaks volumes, doesn't it?
It really does.
And scientifically, it's an iron meteorite, a siderite, so mostly an iron-nickel alloy. That makes it quite distinct from, say, stony meteorites, which are more common overall. Specifically, it falls into the IAB group of iron meteorites. That's a classification based on its chemical makeup and structure.
Yeah.
It tells scientists these meteorites likely shared a parent body or a similar origin story.
And it feels unique, too, that weight. Why is it so dense? And the way magnets just leap onto it, that must make finding them way easier.
Absolutely. The high metal content is key. That's the density. That's the strong magnetism. And yes, a huge help for discovery, especially using metal detectors. Now think about their journey. Coming through the atmosphere, they often get this dark fusion crust.
Like a scorch mark.
Exactly, a burned layer. And sometimes regmaglypts, these like thumbprint-style pits carved by the superheated air rushing past. But, after thousands of years sitting on Earth, those features can get weathered away. Which brings up a really interesting point.
Yeah.
How does something that survives space, that survives fiery atmospheric entry, how does it then become so vulnerable once it's just sitting here on Earth?
That's a fantastic question. And it leads to something I found really surprising. Okay, so individual falls of iron meteorites are rarer than stony ones,
Right.
but they make up almost 90% of the total mass of all meteorites ever recovered. How does that work? It seems like a paradox.
It absolutely is a paradox. And it tells us a lot about our collections. See, because they're dense metal, they resist breaking up during entry better than stony ones. They often land as big chunks.
Bigger pieces survive.
Bigger pieces, plus they're strongly magnetic, so metal detectors pick them up easily. So they're overrepresented in our collections simply because they survived the trip better, and we're better at finding them. It means our collections might reflect survivability and findability, more than the actual ratio of what's falling. For Campo del Cielo, that iron nature was crucial. We've recovered over 100 tons.
Wow. And that time on Earth, that weathering process, you called it terrestrialization, that's what gives them that unique look, right? The irregular kind of rounded shape.
Exactly. It smooths away the sharp edges, the flight marks, and creates this natural patina. Sometimes people describe it as like a coal patina with bright platinum highlights. It's the meeting point of its cosmic past and its long earthly history.
Okay, so this part really gets me. Where did these colossal iron chunks actually come from billions of years ago?
Right, so iron meteorites like Campo del Cielo, they're essentially pieces of the cores, the metallic centers, of early small planetary bodies. We call them planetesimals.
Like baby planets, sort of, yeah.
Yeah.
Building blocks. These planetesimals, like Earth later, got hot enough inside to melt and differentiate. That means the heavier stuff, the metal, sank to the middle, forming a core. Now, most iron meteorites probably come from the cores of asteroids that fully differentiated like that. But Campo del Cielo and the other IABs, they're a bit different. The thinking is they might have formed closer to the surface of a metal-rich, more primitive body, maybe after a really huge collision.
So a more complex story.
Or a more complex, possibly more violent origin, yeah.
Yeah.
Not just a simple core fragment.
Okay, so originating out in the asteroid belt between Mars and Jupiter. Let's jump forward to their arrival here, the impact. When did that actually happen?
We think the main impact event was roughly 4,000 to 5,000 years ago, but we have something even more precise.
Oh, yeah.
Carbon-14 dating. They found charcoal, burnt wood, right at the impact site. This wood came from a forest fire that was directly caused by the impact.
And that dates it very nicely to 500-800 years ago, give or take about 200 years. It's scientifically robust, and it really paints a picture of the immediate environmental devastation.
And it wasn't just one big rock hitting the ground, was it? Tell us about the impact site itself.
No, definitely not one piece. The site's in Argentina, spanning the Chaco and Santiago del Estero provinces. It's this enormous impact strewn field.
Strewn field, meaning scattered pieces.
Exactly, scattered over a huge area, at least 3 kilometers wide by 20 kilometers long. Some sources suggest it could be way bigger, maybe 100 kilometers by 30. And within that area, there are at least 26 confirmed craters. The biggest one is massive, about 115 by 91 meters. Think a football field, roughly.
Good grief.
And in some craters, they found melted silica glass. That's clear evidence of a massive explosion on impact. It basically flash melted the ground.
So the original object before it hit the atmosphere must have been gigantic.
Oh, absolutely enormous. Estimates put it at over 4 meters in diameter, maybe bigger. It broke apart, fragmented as it plunged through the atmosphere. That's why we find pieces scattered over such a vast area. And here's something interesting about Campo del Cielo specifically. It has what scientists call an unusually high inclusion density for an iron meteorite.
Inclusions, like bits of other stuff inside the metal.
Exactly. Pockets of different minerals embedded within the iron-nickel matrix. These inclusions can actually create weak points, even in solid metal. So it's possible these numerous inclusions made Campo del Cielo more prone to shattering during atmospheric entry. It might explain why it broke up so dramatically and spread so widely.
Fascinating. So beyond the impact drama, what are these rocks telling us, scientifically speaking, about the early universe?
Oh, they're incredible storytellers. Chemically, the bulk is iron, about 92.6%, then nickel, around 6.7%, and a bit of cobalt, less than 0.5%. And that nickel content being over 5%, that's actually a key giveaway. It's how you can immediately distinguish meteoritic iron from, man-made iron. It confirms it's not from Earth.
Right, but it's the really tiny amounts of other stuff that hold the biggest clues, isn't it? This idea of a chemical fingerprint.
Precisely. It's the trace elements. Things like phosphorus, germanium, gallium, iridium, elements measured in parts per million. These elements are what we call sierrophile, meaning iron-loving. They dissolve easily in molten iron, or chalcophile, sulfur-loving. Their specific amounts, their relative concentrations, create this unique chemical fingerprint for the IAB group. It's not just a label, it's a direct record.
A record of what, exactly?
A record of the conditions and the chemical processes happening inside their parent body billions of years ago in the very early solar system. For planetary scientists, it's like having a piece of that environment right here. It helps us piece together how planets, including our own, actually formed. It's like a cosmic Rosetta Stone.
And then there's what happens when you actually cut one open. That pattern you see isn't just for looks, is it?
Not at all. That's the Widmanstätten pattern. You see it when you slice an iron meteorite, polish it, and then etch it with a mild acid.
It's beautiful, that crystalline structure.
It is stunning, but it's also pure scientific gold. That intricate pattern is formed by the intergrowth of different iron-nickel alloys, specifically camosite and taenite, which have different nickel contents. And here's the key. That pattern could only form if the metal cooled incredibly slowly. We're talking maybe a few degrees Celsius over millions of years.
Millions of years.
Yes. That kind of slow cooling can only happen deep inside a large body, an asteroid core, insulated from the cold of space. The width of the bands of the pattern, the lamellae, tells us how slowly it cooled, which gives clues about the size of the parent body and its thermal history.
That's incredible. You're basically reading ancient geological processes from billions of years ago just by looking inside this rock.
Exactly. It turns the meteorite into a tangible piece of planetary formation history. You're holding evidence of core formation right there.
Amazing. Okay, so shifting gears a bit, these things literally fell from the sky. Who found them first? And how did people understand them over time?
Well, this is crucial. Indigenous peoples in the region knew about these objects for, potentially thousands of years before any European documented them in 1576.
Right, long before.
They called the area Pigam nan Ralta, which also means heaven's field. They had legends, stories of iron rain coming from angered gods. There's evidence of pre-Columbian pilgrimage routes to the area. They seem to have associated the iron masses with some kind of sun cult, believing the iron actually separated from the sun.
From the sun itself.
That seems to be the belief, yeah. There are even legends about the meteorite transforming into a bright and shining tree at dawn. It shows a deep, long-standing cultural connection and reverence.
So what happened when European explorers showed up?
Well, the Spanish first documented them publicly in 1576. But they weren't looking for meteorites. They were searching for silver. They initially thought it was just an iron mine.
They didn't realize it was from space.
Not at all. Not then. Even much later, a formal expedition in 1783 looked at a large mass and concluded it was just a volcanic formation. It wasn't until samples were analyzed chemically finding that distinct high nickel content, 90% iron, 10% nickel roughly, that its meteoritic nature was scientifically confirmed.
That's fascinating. You mentioned the Egyptians knew iron came from the sky.
Yes. It's a really interesting historical point. Ancient cultures, like the Egyptians, clearly associated iron, especially early finds, with the heavens. The word for iron sometimes related to sky or star. They knew it came from above.
But that knowledge was somehow lost.
It seems it was largely lost to sort of mainstream European thought. The idea that rocks could fall from the sky was actually debated fiercely and only really accepted scientifically in the late 18th, early 19th century. So it was a rediscovery, in a way. Science doesn't always move forward linearly.
So you see this complete transformation in value from maybe a source of silver to something deeply spiritual for indigenous peoples, and then finally recognized for its huge scientific importance. How much of this stuff have we actually found?
An incredible amount. Over 100 tons of Campo del Cielo material has been recovered so far. That makes it one of the heaviest meteorite finds anywhere in the world.
100 tons. Any famous big pieces?
Oh, yes. El Chaco is probably the most famous historically. Found in 1969, it weighed 28.84 tons. At the time, it was the second heaviest single meteorite ever recovered globally. But then more recently, in 2016, they uncovered Gancedo. That one tips the scales at 30.8 tons, making it the new heavyweight champion for Campo del Cielo.
Incredible sizes.
Absolutely. And Argentina recognized the importance. In 2008, they passed a law banning the export of these meteorites. It signals a national understanding of their scientific and heritage value, moving beyond just seeing them as, commercial objects.
So you really have these two discoveries, don't you? The deep, long-term understanding by indigenous cultures, and then the later European scientific discovery, which initially got it wrong. It really shows how value changes across time and cultures.
Precisely. And looking even broader historically, in Mesopotamia, Sumerians, Akkadians, they used meteoric iron, they called it ambar, for sacred objects, long before they figured out how to smelt iron from earth ores. And Egypt, as we touched on that link to royalty and power, King Tutankhamun's dagger, famously made of meteoritic iron, confirmed by analysis.
A dagger from the sky.
Literally. Their texts connected iron and the sky. They seemed to know its origin, knowledge that faded for centuries. Of course, that ancient reverence is different from, say, modern New Age beliefs attributing healing powers to meteorites. Those are more recent cultural interpretations, not scientific ones.
Right. Okay, let's talk preservation. It feels so weird. These things survived, plunging through the atmosphere, this incredibly violent event.
Yep.
Yet once they land, you're saying they're actually quite fragile. How can something that tough be so delicate on Earth?
It's all about the change in environment. They're incredibly tough against mechanical forces, the shock of entry. But on Earth, they meet their nemesis, water and oxygen.
Rust.
Exactly. Rusting, oxidation. Space is a vacuum, essentially. No moisture, no free oxygen.
Yeah.
Earth is wet and oxygen-rich. Liquid water is the big enemy. Even just changes in temperature causing condensation on the surface can kickstart corrosion. It really underscores how different the terrestrial environment is from space. What protects them out there makes them vulnerable here.
So if you have one, or if a museum does, what's the key to keeping these pieces of cosmic history safe? For science, for future generations.
Rule number one, absolutely critical. Keep them dry. That is paramount.
How do you do that? Move to a desert?
Well, living in a dry climate helps.
Mm-hmm.
But realistically, it means using desiccants, those little packets that absorb moisture in storage containers, or maintaining a very stable temperature to prevent any condensation forming on the cool metal surface. Beyond keeping them dry, a protective coating is usually recommended. Surprisingly, something simple like ordinary mineral oil, even clean motor oil, applied thinly with a soft cloth, works very well for stable long-term protection.
Not WD-40.
Definitely avoid thin, penetrating oils like WD-40. They don't offer lasting protection and can sometimes carry moisture in. Also, avoid clear paints or lacquers. They might seem like a good idea, but they seal things in, can yellow over time, and are incredibly difficult to remove later without potentially damaging the meteorite. And preparation is key. Before you put any coating on, the meteorite has to be perfectly clean and dry.
How do you clean it?
Don't touch it with bare hands. The oils and acids from your skin can cause etching over time. Use gloves. Clean it gently with a solvent that dissolves grease and oil, something like acetone or even paint thinner, carefully applied. Then let it dry completely if there's already some rust. Soaking it in pure alcohol like isopropyl alcohol for a while can help dehydrate the rust, then brush it off gently once dry. And the absolute never ever use tap water. It contains chlorine and other chemicals that can seep inside and cause long-term internal corrosion, which is disastrous.
Right.
And never seal it tightly in a plastic bag. You might think you're protecting it, but you're actually trapping any moisture inside, right against the metal, creating a perfect little rust incubator.
So it needs to breathe in a dry environment.
Exactly. No, it's true. Some Campo pieces found in higher, drier parts of the strewn field are naturally better preserved.
Yeah.
Less groundwater exposure. But for most pieces, especially in collections, active, careful human intervention, good stewardship is absolutely vital.
Okay, so let's wrap this up. Campo del Cielo. It's clearly so much more than just a heavy, dark rock. It's a direct link to the ancient solar system. Tangible proof of how planets formed, how cores differentiated. And the sheer amount recovered, over 100 tons, plus its documented history. It makes it globally important scientifically and historically.
Absolutely. Studying these pieces tells us so much about cosmic chemistry, about the physics of entering our atmosphere, about those planetesimal processes billions of years ago. And as we've discussed, the cultural impact is just as profound. From those ancient legends of iron rain to how it shaped our scientific understanding of the cosmos. It's a rich story.
So what's the takeaway for you listening?
Well, the continued study and critically, the proper preservation of these amazing objects is just essential. For future science, yes, but also just to keep that sense of awe and wonder about the universe alive. And maybe here's a final thought to leave you with. Isn't it fascinating that the very thing that helped these meteorites survive their fiery journey, that incredible metallic strength and density, is also what makes them so uniquely vulnerable to decay once they land here on our wet, oxygen-filled planet? What does that tell us about the power of Earth's environment, maybe? How it changes everything that arrives? And just how delicate the task is of preserving these incredible messages from the cosmos.